Okay, I need to apologize because I didn't record the meeting. So, okay, first I explain the intermediate value theorem. This is still chapter 2, still in the limit chapters. So imagine you have a graph, okay? You have an interval from A to B, okay? This is your point A and your point B, okay? And you have this is the point, this is the B point, this is the function. It can be actually anything. So if I draw this part like any functions, like for example this function, yeah, I can do that also. This is just an illustration. So if you have any function here and you have the interval a and b, and you define that f is continuous over a closed interval a b, so the function will take any value between the value of fa and fb, okay? It means for any value L, okay, and the L is between the FA and FB, okay. So if I draw the C here in the middle of AB, I will have my exact L is here, okay. So it was saying that the L is in between of FA and FB, okay. So what does this value theorem or intermediate value theorem say is, if you have any interval and the function between those intervals is continuous, so every point in those intervals will be having a value of, in y-axis, the L value will be in between FA and FB, okay. So for example, if you have, okay, the use the intermediate value theorem to show that there's a root of given equation on specified interval, okay. So this is the function, this is the interval, okay. First you need to evaluate a and b, okay. So this is having negative sign, this is positive sign from our calculation. And if you see here, we don't really need, okay, we don't really need the graph, okay. We only need the point, okay. So the point A is here, the point B is here, okay. So what does it say is, if I have positive and negative at the end of my functions, so there will be a point that will have 0, okay, here. So I will have C, and when I plug in C in my function, it will be 0, and that is definition of our root, right? At least you have these conditions, okay. So through our value theorem, intermediate value theorem, we will have at least one root here in between of closed interval 3 and 5, okay. And if this is the calculation, if you want to estimate or evaluate what is the C here, okay, this is 4, okay. Okay. And the next part is I want to give some explanation about what I've sent to you, okay. So I have sent PDF files. It is chapter 1, chapter 2, okay. What I've sent to you is from 8th edition, okay, 8th edition of calculus, okay. In 8th editions, the chapter 1 is function and limit, and chapter 2 is derivative, okay. But our course is using 9th edition, in which in our chapter 1 here is only function, chapter 2 is limit, and chapter 3 is derivative, okay. This is just to make sure that what I've sent to you is the 8th edition, so you can start to have exercise in this function unlimited chapter 1, and later if we have tackled several problems in derivative, you can also check the chapter derivatives. Okay, and next quiz I will announce later. Maybe I will announce on next Monday. Okay, so what I've taught in the class, you can try to solve this. I mentioned this in the class, but I think you can try by yourself. Okay, you can try by yourself and remembering the steps. Okay, the key is to have this. Okay, this is, or we have proven that. And if we have another, like, this is also true. Okay, so you can try to solve all the problem here. Okay, I will not give you the step-by-step solutions. You can ask your friend if you want, but I will skip this for now. This is just some example exercise. I'll go directly to derivative. Okay, so derivatives. Okay, if you imagine yourself running around the jogging track, okay, I believe if this is time and this is distance, this is the graph of your position, okay, over the time. So you have maybe f of x, or maybe st, because it's position, but let's stick to f of x. Okay, so this is your obviously, or maybe approximately the illustration when you are running. Okay, so here the tangent is increasing. Okay, but after that the tangent is decreasing. Okay, so what is really happening is, maybe at this part it's getting faster and getting slower. The distance traveled is changing, right? Okay, so you are getting faster, and then maybe at some point you will get tired and then slower. Okay, makes sense, right? Okay, so okay, if we zoom in, okay, let's just take this triangle. Okay, let's say this is delta y and this is delta x. Okay, if we try to zoom in and see what does it mean if we have our definition of limit as delta x closer to 0 as our ratio of this delta y and delta x, the tangent. Okay, roughly we can say that when x is getting smaller, let me change the color. When x is getting smaller and smaller, the triangle getting smaller. Let me try if it's getting smaller like that. Okay, when it's getting smaller, we will have annotations or approach that this means this part is infinitely small changes. Okay, and remember that the derivative means in physical means is the instant slope or velocity if you are illustrating with the running or movement. Okay, so this instant slope at that point, at this point, okay, at this point, at the moment, that is our derivative. Okay. Okay. And we can see from if we have graph like this. Let me make more curvier. Okay, and then I have this line, the second line here. Let's just say that this is let's just say this is A, this is B. Okay, so this is f of A, this is f of B. Okay, let's see our slope from this part. Okay, from this triangle. Slope is fb minus fa over b minus a. And according to our concept, okay, we will have limit as b approaching a. Okay, so this is our concept of derivatives. Okay, we can also write this as this is h, this is x. Okay, so this is x plus h. Okay, it's also similar meaning. Okay, or I will write here so limit as h going 0, this is our delta y delta x dy dx, and this is our derivative. Okay, so derivative of f. Okay, and then I also give you three conditions. Okay, first like this, second like that, and the third one is like that. So all of these three, okay, this graph, all these three, okay, or I will write this as f is failing to be differentiable. What does it mean? So it means if you have a corner, if you have discontinuity, okay, like this, and you have the vertical tangent, okay, all this function you cannot differentiate. Okay, the concept of differentiability is if you have f prime is defined by, let's go back to the limit form. Okay, f is differentiable at x equals c, then f is continuous at x equals c. If f not continue at x equals c, okay, then f is not differentiable. Okay, I think that's clear and it's more intuitive. Okay, there's some example, but I think you can see it by graph, and let me just skip that for you. And let's go to let's just go here. Okay, if you see from this graph, okay, state the numbers in which f is not differentiable. Okay, if we see graph, this is our discontinuity here, we have a corner here, we have an asymptote here, and this is vertical tangent. Okay, all these four is making the functions not differentiable. Okay, at x equal -4 is discontinuous. As x equal -1 is having a corner. At x equal 2, vertical asymptote. 5, it's vertical tangent. Okay, but remember, okay, this is if we look at the graph. If you don't have any graph, but you have the functions and you have the intervals, you need to try and check the intervals. Okay, and with the functions, you will know whether the number you approach will be having right hand limit equal left hand limit or not. Okay, if you see here from this number -4, if you approach from left and if you approach from right, it has different value. Of course, it will be not discontinuous. Okay, so you need to check. Okay, check the functions, check the interval. Okay, the next one is this power rule. I have this f of x with the power of n. Okay, we know that if we want to derive, it will be n goes here and then -1, right? And this is the derivatives. But we need to apply, okay, our limit definitions into our functions. So if we apply, it will be like this form. Okay, so this is x plus h become x plus h with the power of n. Okay, x with the power of n and over h. Okay, to solve this problem, okay, I need you to remember all this some algebra operations. Okay, or algebra rules. Okay, if you have a squared minus b squared, you can change or you can factorize the a minus b, a plus b, right? If you have cube, you can factorize a minus b, and you make wait, I have wrong here. This should be squared. Okay, so a squared, ab, b squared. Okay, you have 4, you have a cube, a squared b, a b squared, and b cubed. Okay, you can do the same thing for 5, right? You can a4 plus a3b squared plus a2 blah, 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 and etc. And you have the pattern. Okay, you have the pattern. So if you have n, okay, and you want to factorize a minus b, first thing a n minus 1, n minus 2, b, let's just say dot 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 at the very middle, and then you have a, b, n minus 2, b, n minus 1. Okay, so we are using the same thing, using this expansion form or the factorizing form to prove our limit. Okay, let's try to check. Okay, let's just make this is as our a, this is our b, and make the a with the power of n minus b with the power of n, like previously mentioned. Okay, you can have this x plus h minus x, so it's a minus b. Okay, this is a n minus 1. Okay, this is a n minus 2, and then b. Okay, and then this is a, this is b n minus 2, and this is b n minus 1. Okay, and then of course solving x with x, canceling each other, and h is left here, canceling the h with the bottom one, and we have this equation now. So when we plug in 0 to here, it will be x n minus 1. Also here, if we plug in 0, x n minus 2 multiplied by x, it's become plus 1, so x n minus 1, right? And all the same thing here. And how many x n minus 1 there? It's n, okay? The number repeated n times, okay? So we can write this as our conclusion. So it will be our proof that the first derivative of x with the power of n is n, and then x n minus 1. Okay, and the same thing you can do with the this form. Same thing, same approach. Okay, and some rules. You can check this out, and then some product rules and quotient rules that we will describe both of this in the next session.